just project it.
Is there a power strip on the computer station over there?
Probably, but now he's over here already.
Want me to...
Project right there. Ah. Okay. Okay, class started. At least for you. So I'm starting to walk now. This is good. But I've had this thing for over a month now. So now it's kind of shifted because I lean on the left side to make sure I can actually even walk. Now the foot is okay, but the knee is starting to go bad again. And so let me talk to you about my knee. Because there's a point to my knee. It's kind of cool. It's extremely cool. I mean, it is cool. So one time, this is, there it is, this is my knee right here, okay? And then there's two bones coming down here, one bone coming down here, two bones coming here, okay? Those of you guys who have wives who are doctors, you can tell me I'm wrong. But the big thing coming down is called the femur, and the femur bone connected to the knee bone, and the knee bone connected to the two bones down here. And so here's the femur comes down like this, and you know how the bone kind of ends like this, right? It goes up in the hips up there. And one day, we're a family that plays together. I have a couple of sons, a couple of wives, whatever. No, we have one. And then before this happened, all three of them used to admire and worship me. But one day, we're a family that plays together. And one thing we do together is run. We run quite a bit. And we run 5Ks, 10Ks, and all kinds of things. We do triathlon. And so one of these time, it was down in Union City. You guys know where that is. It's the Bay Area, right down a little bit below Hayward, Oakland. And they had this thing for Halloween. It's called a Cabbage Patch Run. And we all got there. This time it was a very special run because it wasn't just my family, my wife and I, and my sons. It was my brother's family, also wife and two kids, my sister's family, wife and two kids, and my parents. And my sister's family, the husband brought also his sister's family. So it's a big, huge thing. And I'm very competitive. I'm very competitive. If I have to kill them all to win, I win. So we made a big bet, and I got there, and I was ready. I was ready to eat turkey afterward and spend my money. And all of a sudden, I just fell over. I started falling over. When I screamed, you can hear it from here in Klamath Falls. And I was like, ah! I started screaming. All my family came over and said, quit quitting around, phone. It's almost started the race. I said, I'm not kidding you around. I'm hurt. He's like, what do you mean? I'm hurt. He said, how you hurt? I said, sniper. Sniper. I'm fighting over there. Sniper, sniper. And they started looking at me. Where were you hit? You hit? Everybody's so worried. And I pointed at my knee. And nothing wrong with it. I was like, I got shrapnel in there. I know what shrapnel feels like. I got shrapnel in there. And sure enough, they thought I was kidding around. I don't want to run the race because I was going to lose. So anyway, I came back here the next day. Went to see the doctor, and the doctor asked me what's wrong with me. And I said, I've been shot. I got, So sure enough, he looked at me and he sent me through all these places. And man, this is pretty stuff. They went in there, it's called arthroscopic or something like that, in which they stick one camera in, and they stick a little blade with some kind of device in here, right? It goes in here, it takes picture. And you can see it. As soon as they got through here, this is the outer part of the knee, you can see this. You ever play ping pong and you step on a ping pong ball, and you see the crack? You can see a crack there. So they went in there, they opened the crack, and sure enough, there's a cavern almost an inch in diameter in this side of the bone. Wow. So they peel it out, and sure enough, so it had caved in. It had caved in, and sure enough, I had shrapnel. It was boned in there, rattling around, right? And so they asked the doctor, and a buddy of mine said, what's wrong with me, doc? I said, it could just be cancer. Oh. And bone cancer. So it is. It was a bone tumor. He said, well, it's definitely a bone tumor. Well, what caused it? Oh, cancer. So again, my wife and my kids were like bringing coffee to me and all kinds of things. You know, like, oh God, they're being nice to me. I'm dying. I'm dying. It's a death sentence. My whole family came up to me, you know, bringing me presents and stuff. And I Ray, you're like, you are going to put me in your will, aren't you? But I'll tell you, people who badmouth this hospital over here because it's a small hospital and, you know, the grass is always greener. But right away, it took him 3-4 days or something like that. He came right back and told me, oh, it's benign. You're okay. You're not going to die at least of this thing. You may die of something else, but not of this thing. I said, well, you know, you got to fix me up. I can't walk around with shrapnel in my knee all the time. I can't even get up. And they go, don't worry, we'll fix you up. Now, you want it, you know, the easy way or the cool way? I said, the cool way, of course. I mean, if my body can be, you know, sacrifice for science, take it, take me. And they go, yeah, let's do that. Let's not put tungsten or anything cool into you, but we'll do even cooler stuff. We'll take other bones from your body and graft it in there. And I said, that's cool, let's do that. And they go, I said, which one is more painful? Oh, that's what's the most important, right? He says, the cool way. The cool way is much less pain. I say, take the cool way. And so this is what they did to me. So that we had a conversation. He says, first of all, there's some very spongy bone inside the bone. That's called, you know, spongy bone. That, we'll just get it from some dead people somewhere. They donated it to a bank somewhere, and hopefully it's refrigerated. But we'll just take that and we'll stuff it in there like you know, putty. You guys see putty. What's that stuff that kids play with?
Play-Doh?
Oh yeah, Play-Doh. Yeah, we put Play-Doh in your knee here, put it inside. How about this big hole here, Doc? It's like an inch hole here. It says, fear not. Brand new thing we're going to play with you with. We're going to go right up here. We're going to cut 2 small little holes. And stick it in here. I said, that's cool. That will solve this problem. But what about here? Now I'm walking around, there's blood and marrow squirting everywhere for the rest of my life. Isn't that the problem here right now? Is it? He goes, what are you, some kind of quack? He goes, that may be, but this is what we're going to do for you. I'm like, so, you know, guess what happens? So I have 2 holes right now on my knee. But they say, we think that, you know, you will scar up there because it's small enough, it'll scar up, the tissue will scar up, and you'll be okay. I said, no pain? He said, no pain, fine. So I did it, and they did it for me. And it was cool. You know, I thought it was cool. Until a year later, and all of a sudden I started walking like this way. I'm looking down, I was like, whoa! My kneecap, which is here, had shifted over here.
Uh-oh.
You know, they're not God. These guys are just doctors, just new. I understood. But, you know, I came back there, I said, you fix me or I kill you. so he says, fear not, Paul. We didn't know this was going to happen. But yeah, we suspect something like that to happen. So they went in there, and they cut out all my ligaments over here. That way the knee could slide back. I thought that's really cool. But now, what about all the ligaments over here? I have none. And he says, don't worry, you don't need it. And he's been right. You know why I trusted him? Because I built that thing. There's a lot of things in there that's been cut off. And you don't want to really stare inside Pentium or whatever it is, a chip you say. It's a mess. It's a mess in there. But it works. It works. You got to be able to deal with this, all right? And so once in a while, still now, my kneecaps tend to slide over and slide back. That's probably what's happening now. But yeah, after a while, it'll slide back. The body's a wonderful thing, just like that computer. It'll fix itself. And you crash, just unplug it, plug it back in. It'll work. It'll work fine. 65. Let's go to the word 65. Say this was my age, 65, and I asked you to, in 8-bit, we're going to do surgery now. We're going to do surgery now, okay? 8-bit, 65. There's a number 65 in there that's all hosed up. Go in there and find out what's wrong with it. And so 65 base 10 is what? In 8-bit. Okay, so let me tell you right now, 8-bit. A bit means what? Anybody know?
Binary.
Binary, but binary what? Let's go back to your lab. Let's go back to your lab now. Can you touch this bit? We're doing surgery here. We cannot just... Can you touch a bit? Have you touched a bit before? No. Yes, you have. Yesterday you did. Wires. A wire. Right? It's a wire. Isn't it? This is a wire. I will draw the wire, however, drawing the wire is like drawing a 1, so when I do this for binary, that's a bit. Know what it is. It's a wire. Same wire you hooked to a light yesterday, did you not? It's a wire. That's a bit. Okay? Because it's a wire inside the computer, it can only be 0 or 1. That's why they call it a bit. In other number, we call it a digit. A digit will go from 0 to 9. Understand what's going on here? We got to speak in our own lingo here. So that's a bit. 8-bit means there are 8 wires that represent this number 65. Agreed? So inside a computer, that number 65 would be what? So that's why we have to go from 65 to binary. Make sense? In the computer, there's really no 65. Clear? You saw it yesterday. No such thing. It's just a bunch of bits. So let's go see. There's 2 ways of doing it. Okay, there's 2 ways of doing it. The easiest way is because you know. Let's go look at the highest power of 2 in 65. What is 2 to the 1 is close to 65.
6.
2, 4, 2 to the 6, which is the number 64. Let's break it down. 65 is 64, agree? That is why we do it, because 64 is 2 to the 6. Clear? Plus what? The remainder is 1. 1 first, you're right, but 1 is 2 to the 0. So now to switch over, do we have a 1 in the 2 to the 0 spot? Certainly, there's a 1 there, right? How about 2 to the 1 spot? 2 to the, so forget the 0, forget the plus, let me just 2 to the 1 spot, no. 2 to the 2? No. 3? No. 4? No. 5? No. To the 6 you have 1, right? So if you look at this, this is 2 to the 0. Let's go backward. 2 to the 0 is 1, right? 2 to the 1, 2, 3, 4, 5. This that 1 that represents 2 to the 6, no? Right? Agree? So 2 to the 6, which is 64 plus 1 is 65. Is this number 65? Agree? So we went from here to there, right? By doing that. Am I right though? Let's talk surgery. Let's talk surgery. Don't leave things dangling.
Is it only in 7-bit?
Yeah! Yeah! What about if you would give me this answer? If you write this down, this is what I'm going to do to you. I am that doctor. I am that quack. I'm just going to put a 1 there. And I say, that's what you wrote that down. You will never see an erase or anything. I write down and say, you wrong. Does that make sense? I'm the doctor. I can put anything in there. I can put bones in there, but whatever I want. I am the engineer. I am the creator. Make sense? Yeah. Put the 0 there. It's very important. If I tell you it's 8 bits, just like in the lab, you saw the bit, you saw the number, you have to hook it up. Is that clear? If I tell you it's 8 bits, you gotta go see all 8 bits. Just because I leave a blank there, so it's blank. No such thing. Is there such a thing in your mind? Sure. I cannot make your mind. Okay? I can only make that thing. There's one name for that thing. Dummy. Very dumb. Okay. Well, that's how you do it. But what happens if I have a huge number and I don't recognize powers of 2 and stuff? Let me show you one very good way how to do things. Okay. How about 65? Or any number. Okay. Any number. Let me say the number 105. How about 105? Decimal, okay? I want to change decimal 105 to binary, let's say. Okay? We can do the same thing, which is 64, right? 64 plus what? The next one down is 32, right? Right? Make sense? Yes. Let's not do that. There's 2 ways of doing everything, and
the right way and the wrong way?
The right way and the right way. Just like the knee. See, I could have put titanium in there, but that's a painful way. So, the least pain possible. This is actually the least pain possible here, is this. Let's do it first. Because if we do it this way, it's kind of hard. I want to be able to change from this base to any other base. You see that? From base 10 to any other base. Make sense? Mm-hmm. So let me trick you. I want to go from base 10 to base 10. I want to convert base 10 to base 10. Okay? I want to convert from. Can I do that? Sure. Certainly, why not? I can do that. Why not? If I can convert base 10 to base 2, base 10 to, I just did it over there. I can go convert from base 10 to base 10. Let's just do that and you will understand why. To convert base 10 to base 10, the best way to do is to do something. Converting means the computer. Let's go back to the computer, not your eyes. The computer can multiply, divide, subtract, and all that, right? And we're talking about math, so we can do certain function. So my question to you is, let's just use some mathematical function. Do something to that. There's a base. Those are the two numbers you see, right? Do it so that, let's make it even easier here. 125. 125. Do it so that you see this number and this number. You do it. You do some operation. What are the operation? Multiply, divide, and all that. So that I get back. I do it to this number here. This 10. Do something between 125 and 10. I give you back 5. See that? Once you give you back 5, you put 5 down. Now you're left with 12. You do something to 12, we give you back 2, right? 125, you do something between 125 and 10, give you back 5. Take 12, because once you give it back 12, you can take the 5, 12, 2. You see that? You understand that? So what can I do between 125 and the number 10? What do I do to get back to number 5?
You can divide them and take the remainder.
Yeah, there you go. Make sense? Isn't it? You divide 125 by 10, you get a remainder of? 5. And a quotient of? 12, no? You understand the division, right? Yeah. 125 divided by 10 gives you 12 with a remainder of 5. Isn't that correct? How about this? Now you have the 12 here, do you not? What should you do again? By 10 again, you get 2 and 1, no? 1 divided by 10, go into 10, 0 time with a remainder of 1, no? No? You read it upward, you get 125, agree? This you have to understand, right? This is elementary math.
Wait, how did you go from 12 to 2 again?
Divide by 10. You have the 10. 12 divided by 10, remainder of 2. Everybody understand remainder and quotient? That's why they taught you that in the first place. You say, well, what is 12 divided by 10? 1.2. No, it's 1 with the remainder of 2. That 2 is 0.2 because it's 2 divided by 10. Make sense? Remember the math. Remember the math. Because that's what we're doing here. Does that, you understand now? Okay, now let's do it. 125. Or let's go back to 65. It's easier. Or 67. So if I was to do 67, clearly this would be that, right? Okay, if we did everything, that would be 64 plus 3. Plus 2 plus 1 was 3. Now, as I talk just like this, you understand now, right? You won't be confused. When I say this whole thing is 3, you understand why, right? 1, 1 is 3. Or I should say 64 plus 2 plus 1. 67. Either way, you understand what's going on here. As we spend more time, the lingo becomes easier. This is the second time we've gone through this, okay? You start to get the pattern now. I always go through things twice. Okay? We get it? This is the first time. So now I want to go from base 10 to base 2. If I want to go to base 10 to base 10, I divide by 10. I go base 10 to base 2, I divide by 2. It's that simple. Make sense? How about 64 divided by 2? Is equal to? 67. 33, agree? Remainder of? 1. Is that clear? Do it this way. Everybody understand what just happened here? 67 divided by 2, you got? 33, remainder of? 1. Question there. How about 33 divided by 2? 16, remainder of? 1. Remember, this is the 2 to the 0 stuff. Agree? How about 16 divided by 2? 8 divided by 2. 4 divided by 2. 2 divided by 2. 1 divided by 2. Make sense? Always get to the 0 here. Make sense?
That doesn't make sense. 1 divided by 2.
1 divided by 2. 1 divided by 2. How many times does 1 go into 2?
Goes into 0.
0 times. And there's a remainder of
1.
Slow me down if you don't understand. There's no shame. Everybody understand now what's going on? And now read it backward. Why? Because that's the 2 to the 0 spot. Is it the same number?
Yeah.
Make sense? Any question here? Okay, so I should be able to go from decimal to binary like nothing. Back and forth. Any question here? On that note, might as well know what is 2 to the 0 all the way to the 10, right? Don't memorize. Anybody tell you to memorize anything, shoot them. You'll do it enough, you'll get it. Make sense? First to the 7?
128.
Okay. You'll be there, you'll be there. You'll be there. You'll be there by next week. Okay, now let's go back in here. We're going to do surgery. And so instead of a knee, we're talking about a processor. Okay, I still remember when Pentium was the hot thing. When I first started, it was 286. And let's go with Pentium, or even processor now. The first thing they tell you about a processor, they describe, let's use the adjective that describes a processor. 32-bit. Agreed? You guys have heard that, right? It's 32-bit processor. Now, do you know what they mean? What are the 32 bits? Okay, let's go. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. How many so far? Yeah. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4. Right? 16 wires. Clear? So what? 32 wires. So 32 wires. Any question here? And what are those 32 wires used for? Always used to compute. Always. You either move these 32 wires around. This is called data. We're talking about data here, right? You understand why this is a data now? This is data. These numbers. At this point, we're talking about numbers. Clear? What can we do with data? We can add them, subtract them, multiply, or divide. We're just going to stay right there. I'm going to teach you how to do that. Okay? And I'll tell you the rest of it is just that. That's what a computer does. That's why it's called computer. It computes. It may look to you like it does amazing thing, and all it does is move numbers around. And now you know what the numbers are. Do you see that? So in this processor, every time you represent a number, that number is represented in 32 wires. Any question here? Make sense? You felt these wires. You touched them. You saw lights light up. That's all it is in there. Nothing more. Clear? So, let's do this. Go ahead. Let me see. Over there. Brandon, close your eyes. I want you to tell him what number this computer is going to double right now. I want this computer to double a number. I want him to make something that does it. So, Brandon, I want you to double this number, okay? Go ahead, say it. This number.
5,000.
Go ahead. No, not you. You have to listen to us. Write down what he's saying. Go ahead, yeah.
1, 0, 1. It's just on.
You're trying to tell him right now?
On.
Just whatever you see. No, just 1, 0, 1, 1. Just repeat that.
1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1. Okay, the rest of the class, if I erase this, do you remember what that was? No. You want to communicate like this? No. Okay, so again, this is what we do. We're engineers. There are reality, and there are reality that's not reality. Okay? So let's go to this though. Let's just look at numbers. Do you want the lights off?
All right, that's enough. Okay, yeah, Lights off, please. The best thing to do always is not to go look at such a big number. Let's see if we can fix that by using a small number. Let's just say our processor is 4-bit. Can we look at a 4-bit processor and extend it? Okay, make sense? So when I say 4-bit, what does that mean? 4 wires. There it is. 4 wires. Okay. So the first thing we look at right now is, let's go back to, let's just leave the light off a second. When you look at a number, you don't realize it, but you should look at a number, all right? Let's just say if those numbers are base 10. What is the question that should be asked right away is, how many possible numbers of base 10 can be in 4 digit? Given 4 digit, how many different numbers are there? How many? 10,000? 10 to the 4? Are you sure? How about, so this is the best way to do things. Best way to do things. Always go down to the smallest. If you can figure out how many numbers can 1 digit, then you can figure out how many numbers for 4 digits. Clear? How many numbers for 1 digit? Where do you get that? 10, 1. 1 digit to the 1. 10 to the 1 is? 10. 1 digit from 0 to 9 is 10 different numbers, is it not?
Yes.
How about there then? 4 digits. 10 to the 4. Agree? Well, but what is the smallest number?
Zero.
0, 0, 0, 0. 0 would be bad. Because if you say 0, I stick 0 here and I put some numbers here. You see that? Make sense? So it's 0, 0, 0. And the biggest one is 9, 9, 9, 9. And you count all the ones in between them. The total is 10 to the 4. Make sense? Is that clear? You see the lingo here. 1 digit, the total number of numbers with 1 digit is 10 to the 1, which is 10 different numbers. But starting at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is the biggest number, not 10. If 10 is the biggest number, that would be 2 digits. You see that? You see what I'm talking about here? How many total numbers possible in 1 digit? 10. 10 possible numbers. What is the biggest number?
9.
Smallest?
0.
4 digit, what is the biggest number? 9, 9, 9, 9. Smallest?
0.
How many total numbers of numbers?
10.
Make sense? How about here? 4 bits. What is the base? So how many total numbers are there?
2 to the 4.
2 to the 4, right? Which is 16 total numbers. So let's write them down. And remember, I already told you how to write them down. Okay, and then how come it, why is it that way? What are we doing here? We start with 0 and we add 1. Great, listen to that word, add. Add. We'll learn how to add next time. But you see that? Makes sense? Great? So this number here, decimal is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Look at that! The biggest number is always what? The base. The base raised to the digit minus 1. Do you see that? Clear if you guys are into equations and memorizing. Make sense? Now let's go back here. Why do I do that? There it is. 4 bits. Watch this. Isn't this 4-bit here? So if I was to take that 4-bit and just, I don't want 4 bits anymore. I want to use another system. How many total numbers are there in 4 bits? 16. Base 16. You see that? Is that clear? So in base 16 you can have 16 total numbers from 0 to 15. Bad. But F is the same as 15. You see what I'm talking about now, right? Let's go look. This is base 10. If I was to go to base 16, hex or base 16, right? 0 is still, if I see 0, I know it's 0 thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? You can still write it like that, right? Because it's still just one digit. Well, can I just write 10 here?
No.
Because that would be 2 digits. Is that clear? So what do we call it?
A.
But what is A really? It's just a letter A, stands for Alphonse. It's actually 10 here. Make sense? Is that clear? Next one would be?
B. C.
Is that clear? So now, lights please. Do you understand why? Why now? B79F E147. This is the lingo we speak. Go to this address, B79F E197. Correct. There you go. See, it's easier?
Easier.
Make sense? Understand why? However, if I was to go and tell you, oh, go in there and find the letter F, you'd be chopping off the wrong stuff here if you were a surgeon, okay? There's no such thing as a letter F. There are, really, inside there are what? 4 ones. Make sense? The F is only Hollywood. It's for you guys out there. Make sense? Any question here? Okay, let's go on to the next one. I think I've repeated everything except for that division thing, which I'll probably repeat again. But now we're going to go to a brand new place. Okay? Which is not really brand new. You've seen it, you just haven't seen it in terms of as an engineer. So everybody can now go from base 10 to base 16, base 2 and all that. Can you? You really can, huh? Okay, let's go to 65, same number, 67. Can I go to base 16 straight from 67? If I go to base 67 to base 2, I divide by 2. If I want to go to base 16, what should I divide it by?
16.
16, no? Agree? Understand why? I proved it. Once you've proven, done. 67 divided by 16 gives you what? 4. Remainder of 3. Agree? Agree? 4 divided by 16? Split up. That's 4, 3. Watch this, watch this. So is 43 equal to 67?
If you are using 43 base.
What is the base here if I did this? This would be incorrect, right? This would be incorrect.
Yes.
This would be incorrect. But if I did this, is it?
Yes.
It better be because I just did it, is it? This is 3 times 16 to the?
First. 0.
0. Don't forget that 0. 0, very important in computers. 0, very important. 0 plus?
Into the first.
Which is 4 times 16, which is? 64 plus? This is 3 is equal to? Great. Have you seen it? This seems good.
Yes.
How else can I check it? Yeah. Say it, say it.
You can put it into binary.
Or, you have to convert that into binary. I agree. 4, 3, which is what? Right? This is?
0, 0,
0,
0.
1.
Isn't that the same there? It better be. I mean, I told you these things are equal. They must be equal, right? A is equal to B, B is equal to C. A better be equal to C. No? What do you learn algebra for? Make sense?
Yeah.
Or go backward here. How about this? What do you group things in? 4, right? From the minimum, from this out? Right? From the least out, right? You start from here to here. Isn't this 3 and then this 4? Are they the same? Make sense? It may be for some, I guarantee you, 2 days, Saturday and Sunday. You can even watch a U of O and OSU game, whatever it is you guys want, or University of Denver or whatever. You can still get this, okay? And those of you, I mean, yeah. So here it is, there it is. Now, if we were doctors, we can speak doctors together, or an engineer, we can speak it together. How old is Paul? You can say, oh, he's 011000011. You and I, we can understand that. You know how old he is, right? 43. It's kind of geeky, but I'll tell you, those of you guys who have girlfriends, go back, tell them now. You will impress them as of this weekend. This is impressive stuff, man. Come on.
Are you sure about
really?
that?
There you go. It's not. It is not. Therefore, if you are to talk to other people, this is a number that's inside the computer. Clear? That's what the number. If I want to add that to something, that's just what really is being added. But in real life, you actually need this. That is why we have to do this. Make sense? It was just me and you, and once I taught you this, we can just stay right here. Because we cool. We speak each other's lingo. But we can't. There are people out there who have no idea. So, we got to do this. Okay? Having said that, though, let's go look. 1 more year, Fong will be a year older. We learned that from just adding 1. Well, let's just go and add again. One more thing that I'm going to do again. Always put these erasers and chalk so far away. Let's go back to adding. Everybody understand what adding is in decimal. We'll do it over here in decimal. 523. I did this with this class. 62. When we add, we always add how many numbers?
3.
3 numbers. So 3, 0 plus 3 plus 2. How many numbers to come out? 2 numbers. 0, 5. Okay? We'll see in a second here. 0 goes where?
There.
You see that line right there? That line is a wire. Make sense? Yeah. These things are wires. Which is 0, 8. It goes here, 0 here. This is what? 1, 3, right? 3 goes here, 1 goes here. Make sense? Any question there? Okay, let's just stay with 4 bits. 4 bits. What is this? Decimal? What is this in decimal?
5.
You understand why now, right? 1 plus 2 plus? 4 plus 2 plus 1 is? 1, you plus 2 here? It's a 0. 1 plus 4 is? Agree? Good. Better. Better lingo here. Let's add these. Let's add in binary. What is 0 plus 1 plus 1? Good, but if I was just talking normally, what is 0 plus 1 plus 1 in decimal? 2, agree? It's 2 things, 2 chalks, 2 things. What is 2 in binary? Because we are in binary? 1, 0, agree? So the answer is 1, 0, right? 0 goes here.
Carry the 1.
The 1 goes there. It's no different. Make sense? What is 1 plus 1 plus 0? 2 things, which is? 1, 0 still. So the 0 goes here, 1 goes here, right? What is 1 plus 1 plus 1?
1.
How about decimal? 3 things. 3 things, right? Decimal, 1 plus 1 plus 1. That's just normal talk here. We're not even talking anything else. 1 plus 1 plus 1 is 3 things. Agree?
Yeah.
But what is it in binary?
1, 1.
Okay. Now we can say 1, 1. You understand why that 1, 1 come from? Or else you should be memorizing. 1, 1, 1 is 1, 1. What does that mean? Make sense? Here, it actually means 1 thing plus 1 thing plus 1 thing. You have 3 things. 3 things is 1, 1 in binary. That 1 goes there, that 1 goes there. Agree? Make sense? This goes here. 1 here, 0 here. Right? Now I'm just going to do that. 0, 1. Make sense? So 7 plus 5, isn't that 12?
Yeah.
Is that 12?
Yeah.
2 to the 2, which is 4. 2 to the 3, which is 8. 4 plus 8 is 12. Agree?
That's what it makes simple, you know.
Very much so. But you see the two there?
Yeah, but you didn't find the ball. There you go.
Very good. What's your name again? Good job. Any question here on adding? Any question here on adding? You know why adding? What we're doing here, right? That thing better add. Here's the need. Just like my need. Just like my need. It's like, oh, we could put the... No. Let's just use your own part or somebody else's part to fix you instead of using titanium and stuff. Okay? That's what we're going to be doing next week. You realize these are wires, right? I told you that at the beginning. So these are 3 wires.
That's 3 wires?
3 numbers, right? Let's do it again.
Oh.
No? That is 1 wire, that is 1 wire, that is 1 wire. This is called a carry in, you know?
Okay.
These are the 2 numbers, huh? Let me just name it. This one right here is A, this is B, this is carried in. You visualize this now. You seen it. I mean, there's wires and you flip the switch, you see a light light up, no? This could be switch 1, switch 2, switch 3 for all that matter. It would see that. You see the frame of the thing now. Do you understand that? So those are the 3 wires. Carry in A, B, right? If I want to add, then I must make something. As a surgeon, I must make something. What's the output? What is it when you add 2 numbers?
You get 2 numbers.
2 numbers, right? Which is how many wires?
2.
2 wires. 1 wire is called carry out, 1 wire is called sum. Clear? And this wire will go to this bit right here, and the carry out wire will go to the next one. Make sense? Do you see that? So for that first part right there was what? 0, 1, 1, right? Go back to your lab. You flip the switch, and you see what? 0, 1, 1 here, no? Clear? And you do something in here. You do some surgery in here, and what should come out here? 1, 0, no? Is that clear? So is this an adder?
Yeah.
Certainly. You're going to make it yet. I don't know what's in there yet, but is it an adder? I'm telling you to do it. If this was an adder, and this is 0, 1, 1, 0 plus 1 plus 1, that's what this box does. What is the result? Which is 1, 0, no? Agree? That's what I want you to make it so that, make something in here so that the 1, 0 come out here. Clear? If I told you this is a full adder, what if I did this? What should come out here?
0, 1.
Agree? Only one thing. What is one thing? 0, 1, no?
So we're base 10 here.
So base 2. This is base 2.
But on the left side? On the
All
carry
base 2.
in,
1 wire.
all base
1
2.
wire. All base 2. 0 plus 1 plus 0 is how many things?
1 thing.
0, 1. Always 2 answers. Always 2 bit. 0, 1. When you add, how many bits will come out? 2 bits. Make sense? Is 0, 1 one thing? Make sense? But you need this 0. Why? Because it has to go to the next adder. Do you see that? Where does the carry out go? It's got to go somewhere. You see that? You cannot just leave it blank. Do you everybody understand now? Oh, it's 0, so I don't need it. No, no, no. It's there. What if it's 1 the next time? You see it? Make sense? I'm going to say, why are we doing this? Okay. We will do that next week. However, let me say this. Stay right here. What happens if I did this? Put a minus there. If I put a minus there, then I must teach you. I must teach you. That 1 plus 1 is 1, 0, right? But 1 minus 1 is 0. I have to teach you that. Something brand new. Meaning I have to make something brand new here. Clear? I have to make a subtractor. Make sense? Here it is. I'm lazy. Don't want to do it. You will never have to learn how to subtract here. You will have to subtract. But we will not learn how to subtract. Because we will not design a subtractor. Is that clear? We're going to subtract by adding. Okay, so watch this. Let's go back to decimal again. Right here, 7 minus 5. Okay? If I was to teach you 7 minus 5, I have to teach you 7, take away 5, and all that. I'm not going to do that. I'm not going to do that. I'm not going to do that at all. I'm going to do this. This is actually 7 minus 5. I have to teach you how to subtract. So this is 7 minus plus 5. Agreed? Plus 7 minus plus 5. This is what I'm going to do to you. I'm going to have a plus minus 5. Plus 10's complement of minus 5. Watch this. Watch this. What is 10's complement of minus 5? 5, number 5. Right? 1 digit. You see it? 1 digit. You go up to the next. 1 digit goes to the next one is 2 digit. You understand what I just did there? 1 digit goes to 2 digit. The smallest 2-digit number is 10. Right? Go from 5 to 10. Count. 6, just add. Add 1. See how many times you add 1 to become 10? 5 times, right? Did I ever subtract? Never. I just go up until I get 10. So the complements of minus 5 is plus 5. Right? So the 10's complement of minus 5 is plus 5. So I say 7 plus 5. What is 7 plus 5? Remember, just 1 digit. Is the answer 2? Is 7 minus 5 2? Isn't the 2 there? You seem confused. Isn't the 2 there? Do anything. 7 minus 3.
So basically you start at the bottom number and just count up to the biggest
10.
one. And that's how much?
That's the 10's complement of that minus number. Do it again. Give me a number down here. 4. 4 go up to 10 is 6. 7 plus 6 is 1, 3, no? Isn't 7 minus 4, 3? Let's do 2 digits. 500 minus 250, let's say. Right? So now the complement of 250 is 250 go to 1,000, agree? Right? Because it's 4 digit. This is 3 digit, no? From 250 to 1,000 is how much? 750. So instead of subtracting 250, we add 750. Oh, look at that. What'd you get? 250, no? Isn't 500 minus 250, 250?
What do we do with the 1?
It's there. Let's put it there.
Just leave it.
You don't care. You only need 3 digits, right? You're the engineers. You don't want to look at it, don't look at it. But it's there. You know why? Because there's an adder here. The adder always will give you that. Make sense? Just like our doctor said, don't worry, it's not there. Don't worry about it. You don't have it, you don't have to worry about it. Other people have them. They got ligaments and tendons and every kind of thing. Still, I'll tell you, these guys are good. I run 5 miles a day before I have gout. But, you know, I do all kinds of things. I don't got no ligaments over here. None whatsoever. Sometimes I run kind of crooked. That's why they call me the sidewinder. I have many nicknames. If you see me sidewinding, because I kind of walk toward my left, and I say, ooh, I'm a little bit off equilibrium here. I start walking toward my right, and yeah, I seem to zigzag. Any question here? Watch this. Watch how cool this is. That's decimal. I better be able to do it in. How about 7 minus 5? Okay? 7 minus 5. Watch this. 7 minus 5. 7 is 0, 1, 1, 1. 5 is 0, 1, 0, 1. Great? When I do in base 10, I call it 10's complement. And when I do in base 2, I call it 2's complement. What is 5? 0, 1, 0, 1. Watch this. Next week you'll learn to flip things. How do you flip them? You flip things. 0 becomes? 1 becomes? 0 becomes? 1 becomes? 0. Okay, what is a gate called? An inverter. What is that? You put a, just like this right here, you put a, there's a box there, and you hook it in, a 0 go in there, and there's a 1 come out. You guys can understand that, right? So we can do that. We agree we can do that. I will teach you how to add, so everybody agree that you can add 1. So this will become 1, 0, 1, 1. So you flip everything, add 1. There is the 5 complement. Remember, 7 minus 5. So instead of that, what do you put in? 1, 0, 1, 1, right? I'm telling you that. I'm telling you that right now. We'll learn it next week. Okay? Learn it next week. But I showed you how to do a 10's complement. That is a 2's complement. So instead of minus 5, I put in the 2's complement of minus 5. There it is. Don't have to subtract or nothing. Just add. Just add. What is this?
1, 0.
1, 0. What is this?
1, 1.
1, 1. What is this?
7, 1, 0.
What is this?
1, 0.
2. Look at that. 7 minus 5. 2. Never did I subtract. Clear? Did I flip? Did I add? But you know how to add. I have an adder. We'll learn how all this Monday. It's just that why? Why do you have to do it? Why do I do it then? Why don't I just make a subtractor? Because I have to make a subtractor. Do you see that? Can I make a subtractor? Yes, I can make a subtractor. But I don't want to. I have an adder already. That's engineering. We do not do engineering so that it's easy for you. We make it so that that thing is fast and small. Is that clear? I can teach you how to subtract. I can make subtractor, but that thing will still look like a house. Does that make sense? Engineering is how to do things many ways, but pick the way where it's the biggest, well, depends. Smallest for us, it's the smallest and it's the fastest. Unless you want it like in terms of calibers of guns. But for us, smallest and fastest. Depends on what you want. Okay? Here, because you want it small, you don't want to make that subtractor. Also, subtractor, very slow. Whenever you have to lay this stuff out in VLSI, in actual silicon, you'll realize it. You'll realize why I have to learn all this. This is cool. And that I have to make it, I don't have to do so much. You want to do the least possible. Sense? Although the knowledge needs to be big. The knowledge needs to be big. You need to know, learn a lot. Have you learned this? Yes, you have learned it. You just never really learned it. All right? You've seen all this. Really, you've seen all this. Even this, when I show it to you, you will see it. You did this. You did this on the number line. You walk over 7. You walk over 7. How is minus 5? You walk back 5. You get 2. You see that? Nothing more than that here. However, the class is only so long. You can take a graduate class level in this alone. Okay? Wow. So let's not do that here. I will repeat it. At this point, you should be able to do all the homework problems. Okay? In this class, when you have decimal back here, I only need you to know numbers that are 0.5, 0.25, 0.125, up to 2 to the minus 4. Okay? And all the numbers tend to be in that kind of range. If you can't do it, you can't do it. Some things you cannot do. You see that? Clear? And you'll learn more about this next quarter, next year. Yeah, we get you interested. We could teach you all of it right now. This is called floating point, but then it just doesn't fit in. Besides, you need to pay me next quarter too. Or Kensaku, whoever else it is. We can't teach you all of it. We could, we would. Trust me. If you can get a degree in 1 quarter, tell you what, I'll give you a degree in 1 quarter. University of Fong, okay? For 5 minutes, I give you a $5 degree. See you.
Would University of Fong be FU?
Yeah, it's PHU.
Well, it makes more sense with the other.